Good morning, friends. Today we're going to be looking at line integrals, and we're also going to look at the fundamental theorem for line integrals and the three ways to evaluate it. So to start, a line integral lets us measure the accumulation of a function along a curve. So imagine you're walking along a path, and at every point there's a value that you want to measure, and so a line integral adds up all those values along your path. And a line integral comes in two forms, the first being a scalar line integral, and the second being a vector line integral. And so a scalar line integral integrates a scalar function, fxy, over a curve. And for a vector line integral, these involve a vector field and calculate quantities along that. Okay, so for scalar integrals, the formula is this, where fxy is the scalar function and ds is the arc length differential which measures the steps along the curve. So if the curve is parameterized as this, then the formula becomes I'll just rewrite this. Whoops. Okay, so that's your formula, and this reduces the integral to a single variable integral over t. Okay, so we're going to do an example of this. And the question asked, given surface of this function, curve C with geometric equations x of t is equal to t over 2 and y of t is equal to t squared. Oh, that's it. Y of t is equal to t squared. Oh no, it's not. T runs from 0 to 6. Okay, so the first thing we have to do is integrate with respect to t. So I'm gonna write and this is given to us here. I'm going to plug x in, which is given here, which gives me t. And next I'm going to find, put this equation over here, dx dt and dy dt. And that was given to us, and we get 1/2 and dy dt. Okay, so we're told that t runs from 0 to 6, so we're going to evaluate our integral from 0 to 6 and plug these values in. And go ahead and evaluate this integral. I skipped a step here. Okay, and if you were to put that in a calculator, you would get approximately 144.36. So this tells you that this is the area under the curve fxy along the curve C. Okay. So we're gonna do a few more examples. For this next one, C is given by x is equal to 4t and y is equal to 3t, where t runs from 0 to 2. Evaluate this interval. Okay, so same thing. First thing we have to do is convert the curve to a function of t. So once again, that's given to us, and then we're just going to plug in our knowns. It's a 9. Next, find our dx dt and dy dt's. And then plug in and solve. So evaluate from 0 to 2. So our fxy is 9 over 4t. Found that here. Okay, 4 squared plus 3. And that's your answer for that one. Okay, let's do one more example like this. This is what we're given. And it's saying that the curve is the right half of the circle. And from this we know that the radius is 4. So I'm going to draw. Whoops, no, hold on. Okay. Where was I? Okay. So my radius R, the angle T, Y. This is R sine T. Okay. So from here, I got X is 4 cosine T and Y is 4 sine T. And we did that because you have to remember that it's a function of T. And so you use what is given to us to find xy. And that's in terms of T. Okay, so, okay, so just like before, we're gonna find our derivatives. Put this over here. And for evaluating, it doesn't tell us the domain or the interval in which we're evaluating, but we know since this is a half circle that we're going to evaluate from -pi/2 to pi/2. And let's recall, like I mentioned earlier, with the scalar quantity, f of your fxy is your scalar function, and then the ds is the arc length differential, and that's what measures the steps along the curve. So with this problem, we have our arc length differential, which we're going to plug into the equation. Or we have the values to plug in. And distribute. And then we can plug them into our formula. So just write it up to make it more clear. We're evaluating from -pi/2 to 2. And evaluate this. And that's what you get is your answer for that one. So that's how you would do it if you weren't given or weren't given x and y explicitly in the question itself, is you would have to find it as a function of t and then go about solving it as usual. So next, here are some properties of line integrals. You have this first one where it shows that the whole integral can be expressed as a sum of smaller parts. This is written in respect to x or y only, and then these are your parametric forms. And we looked at scalar earlier. We're also going to look at vector line integrals. So for vector line integrals, the formula is this, and you can also express it, which is equal to this, where your vector field is written like this. You have your I component, and then your J component. And then this represents the changes along the curve. And so when you use parameterization, the formula would become, let me say, this, and this simplifies the process to one variable t, similar to how you would do it with a scalar line integral. Okay, so there are your formulas. Just a little bit of a refresher on vector fields there. And then there are 3 ways to evaluate a line integral depending on the problem in the field. So for the first example, or for the first way, it doesn't require a potential function. It'll make more sense when we go over examples, but you're essentially rewriting the curve r of t in terms of a parameter t, and then you use that formula for line integrals. So this method is pretty straightforward, and we'll go over that in a bit. And for the second way, you do have a potential function that you use, and if the vector field is conservative, you can find a potential function f such that f is equal to the gradient. And that is what the fundamental theorem for line integral reduces the problem to, reduces it to that. And then for the third way, for conservative fields, you can replace the given path with any simpler path that connects the same endpoints, since the integral depends only on the endpoints. Okay, so essentially, the fundamental theorem for line integrals states that if the vector field is conservative, then the line integral is path independent and can be evaluated using the formula. Okay, so let's look at an example to tie it all together and make sense of it. So this question asks, evaluate that integral, and if f is conservative, use the fundamental theorem of line integrals, then evaluate using the definition of line integral of a vector field. And this is what is given to us. So to start, we have to check if it is conservative or not. So that's the first step. And recall that it means that f is equal to the gradient. So we have to find the partial derivatives g with respect to x, and then of f with respect to y. So based off that, and we get 2xy, which is equal to 2xy, which is true. So that means that we have a conservative vector field. Okay, so since f is conservative, we have to find the potential function. So since f conservative, find potential function. Just rewriting our components over here. So here I'm just integrating our components. Okay, so now we can write our potential function. And these two are the same. So we can write it as 1/2 x squared y squared plus c. And then perform our integration for that curve using the points from the graph. So this is 3, 3. And we have our origin. So plugging these values into our function, we get this, and then I'm going to factor it, which gives me 81/2. That's our answer using that method. And so this is method number 2. Yes. Okay. Okay, so we're going to do the same example using method number 3, and that's if f is conservative, we can use method number 1, but use a simpler path since f is conservative. It is path independent. Okay, and then method 1 is just the definition of the original method. So we're going to, this is the same graph, it's the same problem, but we can use this path because it's only dependent on the endpoints. And so the first thing we're going to do is rewrite the line xy and let x equal t, y equals t, and then also our domain, which is from 0 to 3. Evaluated from 0 to 3, and a dot these two. And then recall that when you dot, you have the result is a scalar quantity. And you can see that we come out with the same answer, 81/2. Okay, so next we're going to use the same problem using the definition of the original method. So way number 1. So to start with this, I'm going to use 2 different colors. Okay, so I have, I'm going to call this one C2, where we can evaluate them separately. So this one's going to be C1. Okay, so this is what we were given. You're going to start by rewriting it in terms of t. So what's that? C1. And that's from 0 to 2. 0 to 2. And then this is from 2 to 3. Okay, so I cut out, but we're gonna start with C1. So this is what we found, and we're just gonna plug that in to our function, which gives us this. And then r prime of t is the derivative of this. So we just have 1 and then 3/2. And then, as we did before, we're going to plug that in. Value from 0 to 2. We're going to dot the 2. So you dot first component with the first component and the second with the second. Gives you that. Oops. And that equals 18. Okay, so let's do C2 now. Plugging that in. Got R prime T. Dot the 2. Integrate that, and you get (81/2 minus 18). Okay, and now for this we need to now add the 2 components. So C is equal to C1 plus C2. C1 we got 18. I'm gonna add that with 81/2 minus 18. And that gives you 81/2. So that just shows that no matter what method you use, depending on the problem, pick the best one. But if you were to perform all 3 on example like this one, you would get the same answer using all 3 methods. So to wrap it up, line integrals, they give us a way to calculate quantities along curves in both scalar and vector fields. And so by understanding the 3 methods, direct parameterization, using potential functions, or simplifying the path, you can integrate line integral problems. Yeah. And with conservative fields, the fundamental theorem of line integrals provides that shortcut to do that. So hopefully that was useful. Yeah, bye friends.